Hello. Can you hear me okay? Great. It's nice to be here. Exciting times, exploding beer kegs, and I don't know, it's fun. And I just want to say that I love that this conference is named Disobey, because questioning things is kind of the foundation of the hacker mindset in my book. Questioning documentation, questioning protocols, questioning security models, and most important, questioning assumptions. All right, my name is Jonas. I'm a security consultant for Centaur, which is a Swedish company. I've been there for the last 10 years. I've been doing what I do for the last 13 years, I think. I've been hacking everything from web apps to Active Directory to AS400. Talk to me later if you have an AS400. I love them. Nowadays, I tend to focus more on Windows security and Active Directory. Do a bit of red teaming. That's fun, messing with the blue teams. I do code, but I'm not good at it. Sorry about that. The scenario I'm talking about today is a scenario where an attacker has unprivileged access or foothold within an environment, and where a user of an offensive toolset is using that against a target. And we also have the victim, which is, in this case, the user of the system that both the pen tester and attacker is targeting. I'm going to focus on the in-packet example scripts today. It's kind of lame because they're just examples, but they are good enough for the sake of this discussion of trust in offensive security tooling. And also, in-packet tools are still used by both pen testers and attackers today, so it's even more relevant. And I noticed that some of these examples have been ported to other platforms and languages as well. Little disclaimer, this is basically what the maintainers said when I contacted them in November. These are just examples. They are not made for production. All vulnerabilities have not been fixed, and there's no CVs, but I will, supply the projects with changes. Wow, that went back. Right. Sorry. And of course, the code that I wrote to exploit these issues will be released once the PRs are done. And this talk is not about detection. I think that's important because even though I love bypassing AV and EDRs, the in-packet toolset is pretty known. There are a lot of IOCs, and they will be killed right away if you have an AV running on the system. So if you want to be sneaky, don't use the default examples without modifications. And of course, I believe in responsible disclosure, so I contacted all the projects 2 days ago, so they have what they need. All right. So what's in-packet? How many of you are pen testers using in-packet in your daily life? I see few hands. I personally use them sometimes. They're pretty good. They're a collection of Python classes and protocol implementations of mainly protocols that's specific for Windows and Active Directory. They were pretty early with this. There weren't that many other implementations out there. There's just Windows systems, and it's sometimes you want to hack from a different platform. So they implemented SMB, RPC, and every RPC service on top of that, which is pretty awesome if you think about it. You can also use different sorts of authentication. Like you can log in with a password, you can log in with an empty hash that you stole, or you can log in with a ticket that you found on a compromised box, which gives you, as a pen tester or attacker, a lot more flexibility. The example scripts that I will be talking about today are Secretsdump, Smbexec, and PsExec. So let's start with Secretsdump. This is the description from the project itself. It performs various techniques to dump hashes from remote machines without executing any code. So it basically only uses remote registry and stuff like that. It's used for post-exploitation. If you haven't used this tool before, it's what you use when you already compromise an account which has admin privileges on the box, and use it over the network to dump secrets that store within the registry. And here's a few examples of what you get from running this. You get service credentials, because if you configure a service with another account than the built-in system account or service account, you need the clear text password for that account, and that's stored within the registry. You, of course, get the local password hashes, or password hashes for local users. You can try to crack them. If, for example, the local administrator has the same password everywhere, which is not that common anymore since Labs came around. But you can also just pass the hash over the network. The computer account is pretty interesting if you're on a domain join box, because you can use that to create like silver tickets and act as the computer account and do shadow creds and stuff like that. Cache credentials are interactive logons that's cached in a bit better format than just a plain empty hash. So you can, if you have a compromised server and you want to compromise the cache login credentials for admin users that have been logging on that box earlier, you can try to crack this one. So this is a result from running the script. So this is kind of how you use it if you're on a Kali box. And this is how it works. It starts off by enabling the remote registry, get the boot key from the system hive, and the boot key is the encryption key that all the other secrets are obfuscated with. And that's not really restricted. Anyone on the box or with the access to remote registry can access that. Then Inpacket will save the registry hive to a temp file. And this is necessary because the ACL, the access control on the SAM hive is pretty restricted. It's only system that can actually read the information there. So by storing it as a file, and that's an RPC function to do that, it can then access that file over an admin share and then parse that file offline to get the secret information or the sensitive information. And the same thing with the system hive, where all the LSA secrets are, like service accounts and stuff like that. And then it removes the temporary files and disables remote registry. That's how it works. So a little demo. In this case, we have an attacker with only standard user privileges on the box running tools. And we have a pen tester that runs Secretsdump against the target. So to the left, we have the attacker. To the right, we have a low priv user that runs a tool that I wrote. So enables remote registry, dumps the hashes, and as you can see, the temporary files that's stored in system32, that's actually the system and SAM hive, or sorry, the SAM and the security hive. And that's all you need to do the exact same thing as a pen tester in this case. So to demonstrate this, I could have wrote a tool that did this on the box itself, and then continue with the steps to escalate privileges using that information. But I could, in this case, I'd rather just copy the registry hives off the box and use the same Inpacket script, but locally on the registry files, just to prove that I have the same information. What you need there is the boot key, which is accessible from a standard user perspective, in this case using a PowerShell script. And using that, we get the same info. All right, so this is actually a local PrivEsc in a packet. And what happened here is that the tool that I wrote just waits for the temp files to be created in System32, copies those to a different place before they are removed by the Secretsdump script. Get the boot key, of course, you need that. And then dump the local hashes and secrets. And then you can pass the hash of the local administrator, or if it's a domain join machine, you can do the silver ticket attack to impersonate any user on the box. And after discovering this, I noticed that pretty much the exact same behavior and exact same code is ported to different tools. PsExec actually just bundles in packets because it's also a Python tool. Metasploit, of course, it's written in Ruby, so they copy the code row by row, exactly the same behavior. Secretsdump is a .NET port of these tools, a little bit different behavior, different file extension, and so on. So my tool won't work directly. This is how the code looks for Secretsdump when it retrieves a register hive. It creates a random file name with a TMP extension. It proceeds by calling, let me see here, calling the save key to that temp file. And then, since this code is run on the client, it retrieves the temp file through the admin share. The interesting thing is that the documentation in the script says that it's supposed to be saving it in the temp file. But I tried to look as far back as I could in the repo, and I couldn't find any implementation that actually did that. But at least they kind of had the right thought from the beginning. All right, so this is the Secretsdump. They just have a different file extension and store it directly in the Windows directory. But that's also accessible for standard users, so there's no difference. Metasploit use TMP and System32, and this is just a quick demo that it works with Metasploit as well. They actually fixed this yesterday, merged the PR in the repo, so it's fixed now. Right, so the solution is pretty simple. Just put the register hives in the temp directory instead, because the temp directory is kind of a special directory. It allows users to create files. Owners of files have full access, but standard users can't list files. So if you have like a random file name there, it will be really hard for a standard user to guess that file name. That's also a good tip if you're like a red teamer or doing pen tests. Stuff that you put in Windows TMP or temp file is fairly well protected. All right. So this is how the vulnerable version looks. If you look at it in Process Monitor, you can see that like this is the original vulnerable version, putting the temp files in the System32, and the fixed version, put them in the temp directory instead. Pretty simple fix. All right. Moving on to the Smbexec. This is a different tool. It's described as a similar approach to PsExec, which is the next tool I'll be talking about. But basically what it does is lateral movement. You already compromise the machine and you want to execute code, preferably as system. It does so by creating a service at the target. In this case, the service has a fixed name, so not that sneaky. It creates a service and then sets the binary path to the command or a specific command line. The command line actually takes the command that you want to execute and then redirects that to execute.batch. And then it executes that batch file, and the output from the command is redirected to the an output file. This is something that I like to call a poor man's pipe. You redirect output to a file, and then you read the file off the admin share. So this is kind of a simplification of how the service binary path is set up. It echoes the path with some escaping to the execute batch file, and then it executes that in the same command line and deletes it in the same command line. All right, in this scenario, it's the exact same as for Secretsdump. We have an attacker with standard permissions, like standard user on the box, and a penetration tester launching Smbexec towards the target. What you see to the right is a process explorer, and then the attackers running the tool, and to the left we have the pen tester. So the commands executed by the pen tester is executed as system. When you run the tool and try to launch commands, you won't get any output. What you see is that the payload or the command that the attacker wants to run spawns a notepad, which is a child process of a few CMDs. So what happened here? Well, this is a kind of a local privilege escalation as well. The commands are temporarily stored in execute batch. It's in the temp directory, and as you remember, I said before, anyone can create files in the temp directory. Owners have full permissions. So in this case, it's kind of a race condition. Since the path is fixed, the attacker can just create the file. If I do this as a standard user, the standard user is the owner of the file. It creates an opportunistic lock on the file, and this is just to get kind of a callback on when the actual script, the privilege service, is trying to write to that file. Because we want to get into the in-between the service writing the command to the file and executing the file. So the op lock will be released when Smbexec writes the command to execute batch, and then just replace the content with the payload that the attacker wants to run. And that's run with the privileges of the service, which is system. And we're good. So I can demonstrate this in a few simple steps. In this case, it's an admin user that creates a file within the TMP, within the temp file directory, sorry. And as you can see, only system and administrators group have full permissions on that file. If we do the same with a standard user, the standard user will have full permissions. And even though the admin in this case redirects output to the file, the owner is still the standard user. And that's exactly how this little trick exploits Smbexec. The solution in this case is also fairly simple. Just create the batch file somewhere where standard users can't write. And it's also, I think it's good to use a random file name because it solves other issues, but it's not really a fix on its own. This is how it looks when the vulnerable code is executed. Just a bunch of read and write operations to a fixed path. And the fixed version use random file names in the Windows path. All right, moving on to PsExec. This is described as a PsExec-like functionality using a remcom service. And the remcom service is a different open source project, which is about 10 or 13 years old, something like that. This tool is used for lateral movement. It's kind of like Smbexec, but you actually copy a binary to the target and execute it. this is how the original version of PsExec looks like. It's from sysinternals, now Microsoft's. So this is like a signed binary. It's been used for ages at different organizations. So it's pretty handy, even if you just want to escalate to like local system on a box. It's pretty handy. It starts off with extracting a service binary that's stored as a resource within the PsExec executable. It then copies that file to the target using admin shares. It creates a new service, which is called PsExec service. It creates a name pipe with the same name. Name pipes in Windows is kind of like a, yeah, I know what the equivalent of in Linux is, but it's a fairly generic type of object that's accessible over the network as well. And it's kind of integrated within the security system of Windows. So you can set access control on name pipe and so on. It then proceeds with copying a encryption key to the systems, to the Windows directory. And this is actually pretty new. It used to have like I think a fixed encryption, but it was a guy from Tenable a few years ago that found really interesting vulnerabilities in PsExec. And I think this was the solution, because this is what's the key that's actually used to kind of encrypt the traffic that's sent over the name pipe nowadays. It continues to, the client part of PsExec connects to the name pipe. And this is like the command pipe. It sends commands. I know that PsExec have more features than just running code as system, but it then creates a separate pipe, or 3 separate pipes, one for standard in, one for standard out, and one for standard error. That's used to like redirect all the streams to the target. What the hell? Interesting jump there. Not sure what happened. Sorry about that. Right, where were we? Yeah, so now the process has 3 separate pipes. The client waits for the process to exit, and stops the service, removes the service, and removes the service binary. Okay, so the in-packet version of this, I think we could safely say that it was written very long time ago, and it doesn't mimic the exact behavior nowadays. It uses a third-party binary that's called remcom. It's a project called remcom, and it used the remcom service part. And just like PsExec, it bundles that as a resource. It writes that to the target over the admin share. It creates a new service with a random name, because that's apparently what hackers do. Then it creates a name pipe, and it's misspelled originally 13 years ago, so it's not my mistake. It then proceeds to, just like the original, connect to the name pipe, sends commands over the name pipe, creates a separate pipe for each stream to read the output and forward input. It waits for the process to exit, stops the service, deletes the service, and removes the service binary. The interesting thing here is that it's a client that's responsible for all the cleanup. So if we interrupt somewhere in the middle, the service with a random name and a random binary will still be there until the box is restarted. All right, on to the next demo. In this situation, it's a bit different. We still have the pen tester using the tool with local admin privs against the target. The attacker in this case is not on the box, but it's on the same network. It has user credentials, not admin credentials for the box, but it can connect to the target. So to the left, we have the attacker. No, to the left, we have the pen tester. To the right, we have the attacker. So first, I'm just showing that the low priv user can't run the tool itself because it don't have admin credentials on the box. When running as a local admin, you get a shell, you can execute code a system, do all the fun stuff. What happens if you run a modified version of the client is that you can just connect to the same pipe as a standard user, while the pen tester is owning the box. You can own the box. And of course, then you need to connect to that pipe at the same time as a pen tester. But then again, if a pen tester is disconnected right in the middle of a PsExec session like this, the service will still be there running. The pipe is accessible until the box is restarted. And this is actually pretty bad, I'd say. And even though you do a different connection, the service will be named differently. The binaries will be different. And the old pipe with the old service will still be there, functioning, exposing the box to any user within the domain often. All right, so this is what went wrong. The remcom service, surprise, the 10-year-old service is not up to key with security. It actually allows everyone to read-write to the name pipe, the command pipe. And this means that the pipe is exposed to authenticated users. And if you manage to configure a Windows box to allow anonymous access, that will also be covered, but it's not that common anymore. During an active session and after interrupted sessions. So this is what the access control list looks on the pipe if you use access check from sysinternals. You can clearly see that everyone has read-write access. If you compare that to PsExec from sysinternals, they only allow administrators to connect. And if you just create a named pipe and listen, the default ACL allows administrators to write and I think users to read and list. So this is actually worse than the defaults. There's another scenario, of course, if you expose the name pipe to remote clients, you also expose it to the local machines or any attacker with the local unprivileged access to the system. In this case, I just rewrote the original remcom client part to exploit the same scenario. With standard user rights, you can't start any service or do anything. With a PsExec session running, you can escalate privileges as well. Not very surprising. All right. So if we look at the code of PsExec, you have a large chunk of hex binary, which is the binary representation of the remcom service. That's actually just decoded and written to the target. If you look at the remcom service itself, you can see this call, which actually sets the security descriptor for the pipe. It uses a null for the discretionary access list. If you check the documentation, we can see that null means allows all access to the object. So it's probably a pretty easy fix, even though I don't know it's worth fixing 10-year-old code. But if you just commented this code out, it wouldn't be vulnerable. If you rewrote it to actually just add local administrators to the pipe, then it would be the equivalent of the system internals version of PsExec. So the solution is pretty simple. Just lock down write access to the command pipe, and we're good. OK. So in packet was vulnerable this way. What went wrong? Well, let's just take a step back and look what this means. It's basically a question about trust and operational security for when you compromise your customer systems. You don't want to introduce new vulnerabilities. You don't want an attacker with access to the system to be able to exploit your behavior and your tools for their benefit. And this is not an academic viewpoint of this. This is kind of just how we discuss it in my team. We've been playing around with doing code reviews of public tools, doing custom builds, and so on. And it gets pretty messy pretty fast. It takes a lot of time to do this, even though it's your responsibility to keep your tool set up to date and secure. If you look at code reviews, what are you looking at when you're actually reviewing code of your offensive tools? Well, first of all, you don't want backdoors in your tools. If you're talking about exploits, it's not uncommon that someone kind of social engineers security researchers to run code on their boxes. I wouldn't say that backdoors is like the largest threat when you work with tools. There are external dependencies. I mean, if you see a Python script that just downloads stuff from GitHub and runs it, that behavior can, of course, change at any time. So that's not really a behavior that you want in your tools. Same thing with binary artifacts. If you like bundle a .NET DLL or something like that, it's hard for you to audit it. You can find out what DLL is, audit the source, and then rebuild it yourself. And of course, when you're talking about communication, there's always the matter of bad OPSEC practices. Are we doing this securely? Are we leaving any sensitive information behind? Are we connecting to the C2 server in a secure way, and so on? And of course, vulnerabilities as well. This is just software as anything else. And of course, software will be insecure. Within packets, it's basically 3 of these that went wrong. They had binary artifacts embedded in the Python code. Even though you can, of course, rebuild the Remcom service yourself and bundle that. But it's still hard for people to audit. I don't know if the behavior of Secretsdump and PsExec or Smbexec goes under bad OPSEC practices or vulnerabilities. Probably somewhere in between. The PsExec, the name pipe issue is definitely a vulnerability. What about, how should you build your tools? You should obviously not just download and run shit from the internet, because that's not responsible if you work as a pen tester. If you go one step further and download the source and build it yourself, it's not much better. You still need to audit the code so you know what it's doing. You can also, if you're talking about audit every version and every update of public tooling that's out there, it gets pretty messy pretty fast. It's a lot of updates, it's a lot of code. So that's kind of where we got stuck in my team. We have some audited code, but it's still a lot of updates to go through if you want to be really safe. You can also go one step further, like from the public tool sets, just cherry pick the functions and features that you want, and then you don't have to audit the entire tool set, maybe. That would be one way of doing it, or just rewrite everything yourself, if you have the time and resources. One thing that I think it's just as important as looking at the code is just running it in a lab environment. First of all, learn the tool set so you know how to use it and how not to use it. You can monitor the behavior in your lab to see, like with Process Monitor, to see how it actually works and what it leaves behind in the form of artifacts. I know that there are some libraries that are used by Sharphound and other tools that actually leave some artifacts behind that's not that obvious. So if you do red teaming and want to be really sneaky, this is something that's pretty good. And if you do this, you also get the chance to collect indicators of compromise for your customers in the report, or for your blue team if you have one of those to cooperate with. Of course, you can outsource this to a vendor, like for Cobalt Strike. It's a pretty nice tool. Just outsource all the work of doing a fairly advanced C2 framework to someone else and pay them money. What you get from that, of course, is supported software and liability if something would, if the shit hits the fan. They're, of course, not immune to vulnerabilities. I think we've seen that in the last year, where there were some interesting vulnerabilities in the Cobalt Strike console. And of course, you're still left with the question of, do you trust the vendor to do all this? And do you trust the vendor to write secure code? And I don't think there's no answer that fits all here. It's basically about risk management, but for offensive operations. It's probably something that you want to discuss with management and maybe your legal team as well, if you work with customers with the legal teams. It's recommended to establish some sort of rules of engagement when you work with customers, because some customers don't really care what you do or how you do it, but some are really picky, and I think it's not uncommon that you see signs of compromise from other actors when you're in a customer environment, and then it's good to have your rules of engagement and your agreements in place, so you can actually tell the customer that we did this and we didn't do this. I think that's important. And if we're talking about the effort that you put in auditing your own tools, I think in my team we've added somewhere that we have a standard tool set that we use on pretty much every Windows assessment that we do, or red team assessment, and we want to have that tool set audited to some extent, and a repository of binaries that we can trust. But then you kind of save time, and you can focus on doing ad hoc analysis and audits of the new stuff that you need to use. Maybe it's a new tool that you haven't looked at before, and spend a little more time and research on that. And I think we'll add that in a combination of auditing the tools, if it's open source, which it always is, building it ourselves, and then, of course, testing it in the lab as well. There's a few things that I think could, benefit and extend this research. I have a colleague that, I think he found a way to do what Secretsdump is doing without actually touching disk. This is on an ID stage at this point. We don't have a tool set to do this, but it's interesting what you can find when you like poke around and implement your own tools. I think the pen testing community will definitely benefit from someone writing a Python client, maybe with a packet for the real PsExec service part. It plays a lot better with EDRs and antivirus because it's signed and trusted to some extent by customers. The Remcon service definitely sticks out as malicious. It's pretty much considered a lol bin in many organizations. But then I plan to release an Nmap script to find the Remcon service, because if you're a large organization and you have a lot of pen tests going on, I think there could be some free shells running in your environment. The only thing you have to do is basically scan for a specific name pipe with a known name. So it could be kind of fun. All right, that went fast. There's time for questions. Just stand up and wave.